Picture this, your nightly job has been running for 40 minutes. It should take 5. Every morning, the dashboard is late and the cluster bill keeps climbing. You have stared at the code 100 times and you still cannot see why. Here is the good news. Claude can help you find the bottleneck and help you fix it. But there is a catch, and it is the whole point of this lesson. Claude diagnoses from the evidence you hand it. Then you remeasure to prove the win. You will leave with the paste, the evidence workflow, real before and afters, and the guardrails that keep you honest. Take a look at the loop you are about to run on every slow notebook. First you measure, you pull the Spark UI and the explain plan before you change a single line. Then you paste the slow cell plus that evidence and Claude diagnoses the real bottleneck. Then you apply one change, just one, and here is the step. Nobody can skip. You remeasure. If the numbers actually moved, you keep it. If they did not, you revert and try again measure, diagnose change, remeasure. That gate in the middle is what separates a real fix from a hopeful guess. Let me give you the right mental model because it changes everything. Think of Claude as a sharp performance reviewer who can only see what you paste. It cannot reach into your cluster. It cannot open your Spark UI. So until you hand over the evidence, it is blind to the real bottleneck. That means your job is to be the instruments. You read the dials, you copy the metrics, you feed them in, and then Claude reads those numbers faster than you ever could. You are the eyes, it is the brain. That partnership is the whole game. So what actually makes PySpark slow? There are 4 usual suspects and they show up again and again. First, wide shuffles, joins and group bys that move data across the entire cluster. Second, data skew, one partition holds most of the rows, so one task runs forever while the rest finish in seconds. Third, Python user defined functions plus tray collect or to pandas calls. Those drag data back to a single machine or run row by row when a built-in would stay distributed. Learn these 4 phases. Once you can name them, Claude can help you kill them. Step 1. Measure before you touch anything. Open the Spark UI and ask 3 questions. Which stage is slow? How much shuffle is it reading and writing? And are the tasks lopsided? Then run df dot explain to see the physical plan. You are hunting for 2 words. Exchange, which means a shuffle, and broadcast hash join, which means the small site got shipped everywhere. Now write the numbers down. This is your baseline. Every fix you try from here has to beat these numbers or it does not count. Step 2, and this is where most people get a weak answer. Give Claude 4 things, not one. The slow cell, the explain plan, the stage metrics and the data sizes. Then ask a sharp question, what is the bottleneck here? And what is the single highest impact change? Here is the difference. No evidence gets you a generic answer that could fit any notebook. But evidence gets you a targeted diagnosis you can actually test. Paste the proof, get the precision. Take a look at a real before and after. The exploded join before you have a join on a skewed key plus a wide group by. One stage shuffles gigabytes across the cluster and one task grinds for 30 minutes. Claude reads the plan and spots it the dimension table is tiny. There is no reason to shuffle the giant one. So the fix is one wrapped call transactions.join broadcast of dim store on store ID Spark now ships the small site to every node and the big table never moves. One keyword, the shuffle disappears. Step 3. Remeasure. Did it actually work? You rerun the exact same cell, open the Spark UI again and compare against your baseline. Watch the numbers move. Before 30 minutes, 8 gigabytes of shuffle, one task stuck at 30 minutes. After 4 minutes, near zero shuffle and tasks that finish in balance, and the explain plan tells the same story. It now reads broadcast hash join instead of exchange. The shuffle is gone, that is roughly 7 times faster, and it is proven, not claimed. This is the slide you screenshot for your stand-up. Let me walk you through diagnosing a sneakier one, the skewed partition. Here is the symptom in the Spark UI. 199 tasks finish in seconds, and one runs for 20 minutes. That lonely long task is the tell. The cause is a hotkey, one store or one null value, holding most of the rows. That is classic data skew. So you paste the task time distribution into Claude, and it points straight at the skew and the usual fixes like salting the key or filtering the null. The shape of the problem gives it away. Now, a fix you will reach for constantly. Kill the Python user defined function. Before you have a Python UDF doing string cleanup, row by row. Every single row serializes between the Java engine and Python and back. That round trip is the tax, and it is brutal at scale. Claude rewrites the same logic as built-ins. regexp replace upper trim, those stay inside the engine in the JVM with no per row Python hop. Same output, often several times faster. When a built-in exists, the UDF should not. Here is a different kind of win. Refactoring from one giant cell into clean functions. Before you have a 200-line notebook cell, it loads, joins, cleans, aggregates and writes all in one untestable wall of code. When it is slow, you cannot even tell which part is to blame. Claude breaks it into small named functions. Load orders, enrich, aggregate daily. Each one does a single job. Same logic, now readable, reusable and unit testable. And the best part, the slow step is suddenly easy to find because each step stands on its own. Let me talk about the chore you will finally do, documentation and tests. Ask Claude to generate doc strings, a markdown header that explains what the notebook does, and a data dictionary. Then ask for unit tests on your new functions and push it on edge cases, nulls, duplicates, empty input. Be honest, this is the step every engineer skips when the sprint is tight, but Claude makes it nearly free. The cost drops to a single prompt, and future you debugging this at midnight will be grateful. Now the anti-pattern that catches everyone. Applying the fix without remeasuring. Here's the wrong way. You paste Claude's optimized cell, you watch it run, you assume it is faster and you move on. But here's the reality. A dot cache on a data frame you only use once can hurt. A blind repetition into 1,000 pieces can make it slower, not faster. Confident advice is not a measured win. If you did not recheck the Spark UI, you simply do not know. Assumptions are not numbers. Let me give you the guardrails, because this is where judgment matters. Claude might suggest a config like a shuffle partition setting that is wrong for your cluster size. It can propose an option or an API that does not even exist on your runtime. So verify before you trust, and the hard rule. Never paste secrets, tokens or real customer data into a prompt. Send the shape of the data, not the data itself. 3 checks before you apply anything. Does this exist on my runtime? Does it fit my cluster? Am I about to leak something? Do not outsource your judgment. Let us be clear about the trade-off in production. Speed versus verification time. The diagnosis itself is fast, minutes, sometimes seconds, but measuring before and after is time you do not get to skip. It is non-negotiable. And the net win is still big. Claude reading a physical plan beats you squinting at it, and the remeasure is cheap insurance. Try to save 5 minutes by skipping the remeasure and you risk shipping a regression that costs hours. Pay the small cost, avoid the big one. Here is a quick decision framework. Should Claude even touch this cell? First branch, is it slow and do you have the Spark, UA and explain evidence? Then yes, paste it and diagnose. Second branch, is it messy but it works? Then yes, ask for a behavior preserving refactor and verify the output is identical afterward. Third branch, is it tiny or something you cannot even measure? Then skip it, it is not worth the effort. Optimize what the evidence says is actually slow. Let the numbers pick the target. Let me hand you the workflow card, the one to screenshot. Across the top, the loop, measure with Spark UI and explain, paste the cell plus evidence, let Claude diagnose one change, then apply that one change, remeasure against baseline, and keep it if faster or revert if not, keep the usual suspects in view, shuffle, skew, UDF, collect and to pandas, great uses, diagnosis, refactor, docs and tests, and then never list, never blind apply, never skip the remeasure, never put secrets in a prompt. That card is your whole lesson on one page. Let me show you where this fits in the bigger picture. Your reviewer job just got bigger. Claude compresses the diagnosis, but you still own the measurement, the decision and the verification. Juniors win here. They learn to read Spark UIs faster with explanations on tap, and seniors win too. They clear performance backlogs in a fraction of the time. But notice what stays firmly yours, the instrument reading, the judgment and the proof. That is the engineering. The tool got faster, the responsibility did not move. So here is the whole lesson in one breath. Measure first, let Claude diagnose from the evidence, apply one change, then remeasure to prove the win. Diagnose, fix, remeasure. That loop turns a 40-minute job into a 4-minute one with numbers to back it. And that closes out our Databricks module. Next we cross into Microsoft Fabric and you will see these same instincts, measure, prove, never trust blind, carry right over. Want to go deeper? There is a full course Claude for data engineers linked below. Subscribe for the Spark, Delta and Fabric AI videos and tell me what is your slowest notebook. Drop it in the comments.